Thank you very much, and thanks for coming, everyone, on such a nice afternoon in Berlin. I think you would have other things to do as well in the city. So, today we are going to tell you a little bit about real-world use case and problem that we have been running into with Zoltan at the Hungarian Academy of Sciences, with working with industrial partners and trying to figure out their concrete use cases. So, we would like to give you a little bit of an introduction of the research institute where we used to work together, and Zoltan still works there, and then pose a problem where, what we have been seeing usually with these industrial partners and usually with scaling out the problems that we were trying to solve. And it turns out that data skew was the issue that we have been facing. And even in this very conference, you could see Google talking about it, or you could see New Relic also mentioning it in their talk. This is a fundamental issue in distributed processing, and somehow we should address it. And one of the steps that we can show you here today is how to at least visualize it in Spark and Flink. And then Zoltan is conducting research with other people from the Hungarian Academy of Sciences to actually pose a couple of heuristics of how to tackle data skew and make an adaptive strategy of dealing with it in these systems. Of course, the visualization works both in Flink and Spark, and we would like to show you how much we had to add to the metric system of both Flink and Spark to make it the metrics collectible, and also to visualize them in a way where it's very easy to detect these problems, so later we can face them. So, a little bit of the introduction. I've mentioned that the Hungarian Academy of Sciences is a research institute. We have been working on research projects close to Flink for a number of years. Also, other big data projects pop up very regularly in the group where we work together. One of the current research projects is called the Streamline project. We also had a presentation with other colleagues on one of the findings of Streamline yesterday. And in this very example, it's very useful for us because Streamline also gives us 4 industrial partners, which is a testing ground for most of our findings. And this use case especially we have been seeing in telecommunication use cases. Namely, one of our partners, Ericsson, posed a problem where we didn't really have an issue with the data as far as it was just a toy data set, but as soon we actually got to a real data set, things just started to break. And that's basically the story in the slide. We have seen multiple use cases where we can build the application fairly easily. We can test it on toy data set. And somehow, you start on the cluster, first hour, everything seems fine. You go to sleep, and then it goes down in the middle of the night. Next morning, you are not too happy. So what could be the issue there? And a number of times, it's really not an easy thing to debug. Maybe you found out that you had a couple of straggling reducers, or in the case of a streaming application, maybe a couple of your operators were running just fine, maybe like 20% memory load. You could have been doing much better than that. And some of them, they just blow out their memory and they don't work anymore. So obviously, someone is in the data distribution. And of course, as you could hear in this conference, again, multiple times, someone is in the distribution. So to give an example, which is fairly recent, let's say we wanted to process tweets just after the previous presentation, maybe about the Rio Olympics. And at that very case, if a machine were to process maybe all the tweets that are mentioning Michael Phelps, that machine is a very good candidate for someone who's going to struggle. Of course, for the sake of this presentation, we can name this the Phelps effect. some others like to call it the Madonna effect or the Bieber effect in different settings. But that's basically it. We have a power law-like distribution where most of the keys are actually for just a couple of values, and then we have this very long tail. And the issue is we don't really expose this. We don't really think about this when it comes to the easiest examples. Like one of the main benchmarks that we tend to use that, okay, this MapReduce installation is up and running, is TerraSort. And of course, we generate data for TerraSort with TerraGen. And usually that doesn't end up with a data set like that. Of course, you can perturbate it a little bit, but that's not what you are testing for. But we are at a point of big data systems when you really need to address this. So we should do something about this issue. And basically, the idea is that usually when you just say that you would like to have a grouping, then of course you hash your keys into random buckets. And if you have Michael Phelps and Justin Bieber in the same bucket, then you are going to have even bigger problems. And somehow we should address this. So in this use case that we have seen, is we found out that most of the problems had this characteristics. So in the telco use cases, it was whichever machine had to aggregate all the counters, for example, for a bigger country and stuff like that. And of course, that we have seen that we had to face this issue, and then we had to reason about this issue for our other fellow developers or researchers. And it made a lot of sense to actually try to visualize this on a very granular level. You have already seen a Flink or a Spark interface most likely to visualize the physical plan of a job, because or at least the logical one, sorry. So that's the main difference that we are trying to do here. It's sort of straightforward to visualize the logical one. And some of the cases, because these systems can do some optimizations for you, that's also very valuable. But in this case, you need to go a step further. And that's what the meat of this talk is about. So, and then, given that you already have this visualization, which we are going to build for you in this talk, it would be nice to sort of address the data skew as well. And when I'm going to hand it over to Zoltan, he's going to tell you how to do that with a fairly effective repartitioning strategy. So, one of the interesting questions is, okay, now let's build this visualization tool, but how much does it actually matter whether we are building against Spark or building against Flink? You might already know that these systems actually have different runtimes. And of course, the code base is very different, but they have some fundamental different concepts and the way they are built from the bottom up. And the question that we had is how much this is really affecting such a physical level visualization that we would like to do. Maybe they are pretty much the same, and it's just a naming. Spark likes to call parts of the execution a stage. Flink says vertex or operator chain. Is it just that, or is it something deeper, given that the models are so very different? So let's have a look at these systems just very quickly on the level that we will try to examine them. Of course, Flink is a distributed data flow model and has this streaming engine and runs both streaming and batch on top of a streaming engine. On the other hand, Spark is sort of a little, or in the database world, you would call this a pipelined engine. On the other hand, Spark has much closer to a batched engine or a staged execution engine, where you schedule up one part of your topology, execute that, and when you are finished, then you are going to forward that data and build on a data set. And of course, you might know, maybe that's one of the very reasons why you are sitting here today, that Spark also achieves currently its streaming solution on top of a batch system underneath. So, what does happen if we actually go a step further? Basically, what we would like to examine is these connections here. That's basically the shuffle phase that we would like to dig into, because that's where the data distribution happens. So let's examine that. The issue that we are facing is on the lower right of the side. Maybe at first we started with an even partitioning. Maybe we are doing a streaming job, reading for Kafka, and the Kafka top partitions have been sensibly created, maybe in round robin, so you would get a fairly even partitioning. But then we do a key grouping, and that's the interesting part. That's where the Phelps effect comes to fruit. So then we would have a slow task or another one because of a heavy key. So how does it look in Flink? As we already discussed, it has this pipeline engine, and it has other alternatives that we wanted to point out. That, for example, you can also do a batched execution in Flink if you need to do that in the batch system, or the way it actually schedules tasks, it only schedules, and that was one of the issues that we have to face, that Flink will always schedule you a batch operator as soon as it gets some input. So that means that the batch job is going to dynamically change during execution. That's something that you will have to handle later. And at the same time, if you look at the streaming job, it made more sense for the developers of Flink to just schedule the whole topology right when it gets submitted. So there are these bits and pieces that you have to address down the line. But basically, what you see that, of course, despite those characteristics of each system, and we'll see them for Spark in a moment, you will still see data skew and slow tasks. And of course, the data distribution, especially in a streaming system, that's something that you don't know upfront, so you will have to sort of learn it on the fly in most of the cases and adapt on the fly. So let's have a look at Spark just to have the same counterpart on the other side. The main difference here is that we don't have this pipeline solution, and then we have to wait for each stage to complete. Of course, for example, in the mini batching case, you could technically, for a streaming application, fire up multiple mini batches at the same time. That's, of course, doable. But this is the heart of the model, if you wish. And that's something that we have to understand when we were building the visualization as well. So when looking at the physical execution plan, that was basically the setup that we had. And what we've seen when communicating the results and the ideas, and basically the problem with other developers is you cannot really reason about this and cannot really see this in action until you have a proper visualization plan and a proper interface to actually talk about it. So what we would like to build is the following. It would be really nice to see on the subtask level. So if you have an operator, maybe you have like 6 instances of that running. So then you have 6 subtasks. And then you have a subsequent operator. Maybe then that has 10 subtasks. And you would like to have this on a, well, in Flink terms, on the input channel level. You would like to see the connections and the data flowing through them. And then it would be very useful to see maybe the top 5 heavy keys and how much of the traffic you have there. And with that, I would like to hand it over to Zoltan.
Okay, thank you very much. So, as Martin said, first we wanted to build a very nice visualization tool. First, to be able to understand what is going to happen deep down at the execution level. So first, we have looked into our existing visualization tools that we have for Spark and Flink. And unfortunately, we have discovered that these systems or tools are basically missing all the fine-grained input and output metrics that we would like to see. And these are really not available in most of these systems like Spark, Flink, or other systems. Additionally, we wanted to capture the data characteristics. What do I mean by that? As Martin said, we would like to see distribution of the keys. We would like to see where keys are going from where, of course. And this is very hard to accomplish in a system, of course, even when you, or especially if you have a production system, to have a very lightweight and efficient solution. Because, of course, you don't want to put too much overhead to your system. Additionally, as we have found out that these systems are not able to visualize the physical plan, which we wanted to see. For example, we have a very nice DAG visualization in Spark. And if we put this visualization in contrast to Flink, we'll see that, of course, because we have differences in the models, as you may know, Flink can support iterations natively. The current Flink DAG visualization is a very nice tool compared to the Spark one, where you basically see all the iterations as independent jobs, and this is going to really mess up your head, and you just don't know where to look and where to find the problems. Or of course, you see very little information about your data, about your execution here. So first, we wanted to add a lot of new metrics into Flink, and the current metric collection is basically tied to the serialization stack. Here we collect all the read and all the write metrics, but we have added a lot of additional metrics, and we made the metric collection to be more fine-grained. Additionally, we are not just collecting information on the operator level, but we are additionally collecting information on the input channel level, and we are going to distinguish point-wise all-to-all distribution patterns as well. And this is a very nice example of such a matrix that you can query for later on, for example, for read bytes. Now, as for Spark, we know that we have this global synchronization between the stages. And what's going to happen is that we are going to have a bunch of shuffle block fetches. And of course, here we can distinguish local or remote block fetches as well. In Spark, we are collecting the data characteristics as well on input and on output, on shuffle write and read as well. And this is a very nice example for such a data characteristics where you can see we approximate the distribution of the key or the frequency, and we also have the local block fetching infos available in the REST APIs. Now, you can ask, okay, now that we have this information, but actually how do we approximate the key distributions? How do we collect the data characteristics? And for that, of course, you need to have a very nice scalable sampling solution, and we have developed this solution in contrast to other solutions, but this is very similar to something that you would like to call a counter-based sampling. So we are basically here approximating the key distribution with a strategy that is or should not be sensitive to early or late concept drifts. Let's say, for example, when you have a streaming job, it has to be lightweight and efficient. Of course, we don't want to put too much overhead to the system. We do not want to do less by trying to do more. Additionally, it has to be scalable, and for that we have utilized a very nice backup strategy for that. And I'm going to outline basically the strategy here. Of course, it is much more sophisticated. It can accommodate to batch and streaming as well. So let's see how it works. Basically, we have a histogram, and we are going to approximate the frequencies of the keys in a bunch of counters. And what we are going to do is that we are going to initialize a sampling rate, which is going to be usually 1.0, but it depends, of course, on the strategy and on the use case, because we would like to have an adaptive solution that can accommodate to your data rate and your data flow. So when we have that, it basically represents the probability in which we are going to record any given key into this histogram. And when that happens, we are going to increase the corresponding keys counter with this sampling rate. Now what we are going to do is that we are going to let, of course, the histogram to grow, but after some time, because we are focusing on the heavy keys, on the Phelps, on the Madonnas, and all the Biebers, we are going to utilize our backup strategy here if we see that we would add a lot of keys. So what we're going to do is that if we see that we pass a light boundary, we are going to reduce the frequencies for all the keys with a backup factor, and then we are also going to reduce the sampling rate with the same backup factor. But of course, after that, we are also going to let the histogram to grow a little bit. And if we see that it is going to be really big, we are going to initiate our truncate mechanism. We are going to throw out a bunch of not so prominent keys. And then we are also going to utilize our backup strategy so that we are going to reduce the frequencies for all the keys with the same backup factor that we reduce the sampling rate here. So now that we have all this information, okay, how do we make it available for our visualization and optimization systems? Of course, all these systems have something like a REST API, so we have basically enhanced the Sparks and the Flink REST API for that. So basically, as for Spark, we provide the block fetch information, the data characteristic information of tasks, and as for Flink, basically we provide the communication that occurs between subtasks of vertices. Additionally, we have a bunch of new queries for these APIs. Basically, you can ask, okay, what happened in the last 3 seconds as a visualization or whatever tool that you're providing here. So, and then you are going to have a bunch of task events thrown at you, basically. Okay, now we have arrived to the place where we really would like to show you the visualization. But before we do that, of course, probably most of you have seen a lot of blog posts and papers about how different operators works in this system, like group by or co-group or join or whatever. And you basically saw a lot of edges going around showing or demonstrating the communication between these operators. So what you're going to see is that what happens when these pictures come alive. Okay, so this is the, in the Spark case first, this is the very nice UI of the visualization. And as you see, task events are arriving, and we are deploying a bunch of tasks on different computers. Of course, you can look into what operators have been pipelined there. As you see, we have passed on to a different stage. You can view the communication that occurs. You can look into the task, and you can check out the data distribution. You can look into various points and identify bottlenecks. And this is a very nice tool that we are using extensively, mostly for our optimization engines to test them, and of course to debug our applications and to be able to know what's the problem. So you can zoom in, zoom out. There are a lot of features, and we are constantly improving this visualization. And as you see, we have incorporated it into Spark. So basically, all you need to do is just pick your favorite job from the job UI, and then you are going to have your job visualized real time. So as for Flink.
Yeah, so we also made a video of running this in Flink. So this is the Flink UI that you would usually expect, and I have written an easy Flink job. Then you have the logical interface for that. And one of the little things that I did with this Flink job is actually I made it so that we have a keyed window aggregation. And in the key window aggregation, I only generate 3 specific inputs for that. And what you would see that there is a 0, one instance of the keyed window sum is actually not getting any data. So that's something that the current Flink visualization would also give you. But if you dig one level deeper and would like to visualize that, I think it sort of pops up, and it's way easier to see that the window is not getting any data. But as you see here, that's okay. That as an information that you would have get. But if you see the other inputs as well, that, okay, these are actually the ones that are getting data, they would have the following key distribution, and they have the following connections with the previous operators. So it's a much deeper understanding of what your job is actually doing on a physical level.
Okay, before we close this talk, or before I let Martin to close this talk, I would like to speak about a very nice project that is very dear to me, which is about to tackle data skew somehow. So we were thinking about, okay, now that we know the problem, now that we know how our data actually behave, let's use all this information to actually solve a very old problem in a generic way. So the goal of this project is basically to use all the collected information to handle the data skew dynamically on the fly on any workload, whether it should be batch or streaming. And let's see a few pictures about this, what I'm telling about. So basically, let's say that you have a certain stage, and of course, you don't have this dynamic repartitioning module of ours. So basically, what you're going to see is that because you have Pareto or zip distribution, some of the partitions are going to be very slow, very heavy, because you have all these Bebers and Phelps, and these keys are really going to make the partitions heavy. So that, of course, your system is going to have a lot of stragglers. So what happens when you switch on dynamic repartitioning is that you're going to notice that some of the files key, of course, if the system or the optimization engine sees fit, it is going to send some of the heaviest keys exclusively into one or two partitions, so that you were able to reduce the size of the biggest partition, basically. And what that means, for example, for Spark, if you switch on dynamic repartitioning, this is a very simple music time series. I think it has been done on some Last.fm data. So basically, it can give you a speed up on most of your jobs by a factor of 2 on average. But of course, in this case, none of the Madonnas or Biebers or Phelps were actually colliding into the same partition. When that happens, of course, we can get a much greater impact, so that we can reduce the runtime basically by a factor of 5 or 6. So as for the future plans, of course, we would like to improve the visualization. We would like to add more features. We are going to have a public beta, and I hope your guys are going to love it. So it is going to be available in the near future. Additionally, we would like to adapt this dynamic repartitioning and data awareness optimization to other systems as well, for example, Flink. Additionally, we would like to open PRs against Spark and Flink with these suggested metrics, so that you can use our visualization with these distributed data processing systems or other systems, or just you can just build your own system as well if you like. Now, before I say goodbye, I would like to show you our new visualization that we are building. And this is much more sophisticated, and this is going to be in public beta very soon. So what you're seeing here is that a very complex Spark job, or a bunch of Spark jobs are actually being visualized. Each node can be a Spark stage or a Flink vertex, and this visualization has very nice interfaces to actually connect your favorite system, whatever your own Python pipeline you have. You can connect it onto the system, and the system is going to visualize it for you. Of course, you can dig into the connections, the communications. You can see the data distribution, all the distribution of the different metrics that you have in your system. Okay, now I'm handing over to Martin.
So one of the main things that we have learned from this project that devil is really in the details, especially in these big data systems, and something that we would have never imagined, that such a speed up that we could see with this halving practically the runtime on a parity distributed input data set, just because we had a nice way of making sure that the distribution was adapted dynamically. And of course, data skew remains a big issue, and this is we think that something that the big data community should come together and tackle in the next couple of years. And we hope that we could demonstrate the power of visualization in such cases. So thank you very much for your attention, and the floor is open for questions. We have one here in the front by Jim.
Hi, guys. The thing I'm most familiar with that reminds me of this work is Databricks Cloud have a visualization tool. And I think it works on historical data. Is it, for the Spark stuff, there is a Spark history server. Is it possible to do the visualizations using the history server?
Yes.
And should Flink have one too?
Yeah.
Yeah, the issue there is that Flink doesn't have a history server yet, but if it would propagate, so we could, of course, propagate the same metrics to the Flink history server as well when it gets into the Flink code.
And have people been mostly using this, using the historical data rather than looking at it in real time? Or what's your experience?
Yeah, as for Spark, it is complete. So all the data is completely available in the history server, so that you can basically just visualize your actually completed job. There's no problem in that. But as Martin said, there is the issue with the Flink that it doesn't have a.
Of course, the way you would really conduct such an experiment and analysis is you look at your job right now, it has a problem, and then you look at the historic data to see how that developed and what happened there. So that's usually what we have seen and implemented. Oh, that has a question there. Thank you.
I really just wanted to play with the microphone. So you said a couple times that you could see hotspots in the visualization, which things are causing slowdown and so on. And I didn't really see what you were seeing. What was it that cued you into that?
Yes.
Yeah, so basically the hotspot part was that you can also, when you click onto one of the vertices or stages, you can also see the data distribution, or at least the 3 or 5 top heavy keys yourself as well in the visualization. So it looks very similar to the figures that Zoltan showed when telling you how selecting those keys work, or when he had the diagram. So it will look something like this. So that's actually from there. That's what you would be able to see. That's how you see the hotspots. So it's when you focus on one of these vertices, that's what you see, and that's why we are moving to the new visualization tool, because it's a feature that we would like to add there, that it automatically highlights the ones that are candidates for repartitioning.